In this session, we learn to apply Ohm's law to prove how the resistance of a conductor depends on the length of the conductor and the area of cross section of the conductor. We start with that. Say we imagine a conductor, a cuboidal shaped conductor like this, of length L and area of cross section A. This is area of cross section and length L. And if we maintain a potential difference V here, a current I passes through that, and then the resistance of the conductor R equals V by I. Now, to prove the dependence of resistance on the length of the conductor, we just imagine two such conductors are kept side by side like this, but in perfect contact like this. Two conductors are kept side by side like this. Now the length of first conductor is L, second conductor is L, and potential difference across first conductor is V, second conductor is V, and then say area remains same for those things. In this type of cases, say we want to find out what is the resistance of this combined system of two slabs. So for that I write R dash. Now R dash, according to Ohm's law, the potential difference by current. Say potential difference across two is applied, say V and V. As we know, potential difference is a scalar, it should get added. So V plus V is the potential difference divided by the resistance, say current in the conductor. Current means flow of charges. Observe here, all the charges what passes through first conductor should also pass through the second, because they are they are joined end to end like this. So all the charges passing through the first conductor should pass through the second. That means the current should remain same in both of them. So I write I. So now we can write R dash as 2V by I. But what is V by I? From the first thing, R, the resistance of single conductor to R. Say R, resistance of single conductor. Now R dash, the combined system resistance is 2R. That means here we have changed only the length. Apart from that, nothing has been changed. Potential remains same across each. All those things. Only in this diagram, compared to this diagram, only the length is changed. Therefore, we can simply write what is that change here? As length is changing, R dash or R proportional to length. Here twice the length, so twice the resistance, like that. We can also show it for three conductors. With this, now we think of what about the area dependence. Say we think of like this, just observe. We think of area dependence. For this area dependence, what we do, we just think of a conductor as it is, as we did in the first case, single conductor. But now we divide the single conductor in a different manner, not adding another conductor here. Say, if we divide this area into two, we slice along the length like this, then two conductors will result whose areas are A by 2, but length remains same and potential remains same. Now, for the one particular conductor, one part of the conductor whose area is half of the big conductor, we write the resistance now. This is L, this is V, and this is A by 2. For that, I write R dash as the resistance again. R dash, say if you want, you can take R double dash here, not to confuse with R dash what we used in previous derivation. Say R dash is again V by I. V by I. But observe, V remains same. I means flow of charges. But here, as we have reduced the area to half, only half of the number of charges should pass through, because area A contains large number of free electrons to pass, but half of that area will contains only half of that. Therefore, the current will become now half. That means V I dash I take there, I by 2 is the current now. 2V by I or 2R again. R dash, R double dash is also 2R. That means when we slice the slab to have the area half, we also get again 2R. That means here observe R for area A and 2R for area A by 2. That means as we decrease the area, resistance increase now. Therefore, we can simply say R is inversely proportional to area. Have you observed? Let me go through it once again. R double dash equals to R, but we know R is for A. For 2R, it is only half of the area, A by 2. Therefore, as area increases, resistance decreases. Therefore, R is inversely proportional to area of cross section. So, finally, we have two dependence factors there. Resistance of a conductor proportional to L, resistance of a conductor inversely proportional to area of cross section, L and A. And observe this, you can see in your say houses, where just observe the wires connected to your TV or lighting, they are thin wires. Now just compare the thickness of those wires with the wires connecting to the heaters like geyser, like that. Those geyser wires are heavier, bigger thickness compared to lighting wires or light or television wires. Why? Because heating wires required to carry large current. For that, they should have less resistance. That's why the area of cross section is made less. For lighting purpose and television other purposes, the current is smaller enough. Therefore, they use thickness less wires. And we just now learnt few things like this, just we recollect it. Resistance of a conductor is directly proportional to its length and inversely proportional to its area of cross section. But by using these two ideas, we continue with next concept here. Observe carefully. R is proportional to L by A, combining those two. We can make it a equation by introducing a constant, what you learnt in 10th itself, where rho is the proportionality constant and the rho is called as specific resistance. Specific resistance or specific resistance or simply resistivity. Resistivity. So, how to define resistivity or specific resistance, that we want to learn, and then we can think of other things. But before that, we want to create unit for resistivity. Say from this equation, I write rho equals RA by L. Now we write the units. Say R ohm, area meter square, length meter. Say cancel it. We have ohm meter is the unit as the unit of, say, so we try to define it now. RA by L. Say if area is 1, length is 1, then rho equals R. We define rho by using this. The specific resistance of a conductor is numerically equal to resistance of a conductor of unit length and unit area of cross section. Let me go through it once again. Specific resistance of a conductor is numerically equal to the resistance of the conductor of unit length and unit area of cross section. That's how we define rho. Let me define it once again. Rho is the specific resistance, and it is defined as numerically equal to the resistance of the conductor of unit length and unit area of cross section. Now we try to arrive at Ohm's law in one more form. Just observe, I write Ohm's law. V equals I into R. But R equals rho L by A, and say from E equals minus dV by dL, we can write, say E as V by L, or V as E into L. It's a similar thing what we used in capacitors. Now we write, substitute everything there. For V, EL, I, rho L by A. But observe, we can cancel L there. E, I by A into rho, But I take I by A as J. It is nothing but current density. We call it as current density. J is current density and it is current per unit area, and in fact it is a vector quantity. We take its scalar value here, but current density is a vector quantity and its direction coincides with the field direction, and it is normal to the current. So current density, now we can replace it, and also say instead of before replacing it, we write it like this: E equals J rho. But I take J onto this side and I write E by rho. But E by rho or 1 by rho is, we write it as sigma, and it is called as conductivity. Therefore, J equals sigma E. Observe, this is the vector form of Ohm's law. Because J is a vector, E is a vector, sigma is conductivity, a proportionality constant there. And this is another form of Ohm's law, where current density is equal to the conductivity into electric field. With this, now we start learning a derivation where we derive expression for drift velocity, and then from that we want to derive an expression for the current conductivity. So we start with the first thing like this. We want to derive expression for drift velocity. So we consider a conductor of length L and which has n number of free electrons, and its area of cross section is E, A. Now if we imagine an electron, free electron, which is moving in random direction like this, random motion like that. Now we, among millions and millions of electrons, we take the ith electron. For that, say Vi is the velocity due to random motion, and due to the applied field. Say if we imagine a field is applied in this direction, then the electron acquires some velocity due to the applied field. Therefore, applied field electric field, say applied field velocity we write for the ith electron as Vi after time Ti, after Ti. Therefore, we can write Vi after time Ti as Vi initial velocity plus A into Ti, where Ti is time with which it travels, or in which it travels. A is acceleration, Vi is the initial random velocity. But we know EQ equals F, which is equal to M into A. Here Q is E, EE with minus sign because electron charge is minus, M into A equals minus EE by M. If we substitute that there, we have Vi equals Vi minus EE by M into Ti. But observe, this is for the ith electron. If we want to get for the millions of electrons, we take the average of this. We take the average of that. That means we take Vi from I equals 1 to n and divide it by n, total number of particles there, and sigma Vi I equals 1 to n and divided by n minus, say, E by m sigma I equals 1 to n Ti. But observe, as initial velocity is random, its average is always 0, and the left hand side of this equation we represent by a special symbol Vd, average velocity acquired by the free field, applied field, and average random velocity is taken to be 0 minus Ee by m, and we write average of Ti as tau, what we call as relaxation time. So with this, we got an expression for drift velocity. I write it now once again. Say Vd equals minus Ee by m into tau. Say it minus sign shows only the direction. Drift velocity is in opposite direction to field. If we take the magnitude only, Vd equals Ee by m into tau. E by m into tau. So with this, observe this, we can slightly simplify it. E tau, say I write like this, E tau by m into E. This is the drift velocity expression. And observe here, E tau by m is a constant and it is called as mobility. I write its symbol. E tau by m is denoted by mu and it is called as mobility. Means how much free is the electron to move. So that is denoted by this. Therefore, Vd can be written as mu E. Vd can be written as mu E, or else mu, the mobility, can be defined as Vd by E, or average drift velocity acquired per unit electric field. Average drift velocity acquired per unit electric field is the mobility. So that is the definition of mobility. And observe one peculiar thing about drift velocity. Say drift velocity depends purely on electric field and it is a constant. If as far as electric field is kept constant, drift velocity is also constant. Once drift velocity is constant, how it is possible, we have to think of, because electric field is accelerating the electrons, but because of the large number of electrons, the drift velocity becomes average and it is constant. That's a very important thing. As long as you keep the electric field constant, drift velocity is also constant. That's why we define drift velocity as average velocity acquired by the free electrons due to the applied electric field. That is the definition of a drift velocity. Let me define it once again. Drift velocity is the average velocity acquired by the free electrons due to the applied field in the opposite direction to field, because if you mention the direction, then it should be opposite to field. So, and also now we learned mobility. Mobility is defined as drift velocity acquired per unit electric field. So with these ideas, now we have to proceed on to the derivation of the expression for conductivity. Say we consider a conductor of length L and having n number of free electrons per unit volume, that is also called as carrier density or charge carrier density, and let its length be L and area of cross section be A and potential difference applied is V. The current passing through this is I. Now we want to write expression for current, and from there we want to obtain expression for conductivity. For that we want to write the charge flowing through this in time delta t seconds. Charge flowing through this in delta t seconds can be written as, say using quantization, n into E, where n is number of free electrons constituting the current in this conductor. Say n is number of free electrons per unit volume into A into L will be the volume of this conductor. NaL will give us number of free electrons in this volume at any instant of time, and then E is the total charge there. So this gives us total charge inside the volume of the conductor at any instant. Now, if we go for a small thing there, a small change, I equals Q by T we know. So Q can be written as Q by delta T we take, or else delta Q by delta T. Here also we can make small currents change. So delta Q is written as delta I delta T. Therefore, in any time delta T, amount of charge passing through this unit, this volume of the conductor can be written as, from this idea, NaLe. NaLe is Q delta Q. Therefore, I delta T equals NaLe is the charge passing there. Now, with this, we want to go for next idea. Say I is equal to NaL by delta T into E, but L, the net distance traveled in given time delta T, what can be written as the drift velocity Vd. Therefore, we can simply write I equals Na Vd into E, the drift velocity, but I take I by A onto this side. Therefore, N E Vd we will have, but I by A, as you know, it is current density, Ne Vd. So once we know current density, we substitute for Vd, we'll get the final expression for current density. Say Ne Vd is E tau by m into E. E tau by m into E. Therefore, J equals N E square by m tau into E, or else we can simply write it as J sigma E, where sigma is Ne square tau by m. This is the expression for conductivity, Ne square tau by m, expression for conductivity. Let me go through the derivation once again. Just observe. We have considered a conductor of length L applied with potential V, and current I is passing through it. A is its area of cross section. From quantization of charge, we want to write at any instant what is the number of free electrons in this. Q equals N into E, but N is total number of free electrons in this. For that we have N is charge carrier density per unit volume, that is charge per unit volume, free electrons per unit volume, N, small n, into A into L. A into L gives the volume. N into A into L will give us capital N, the number of free electrons in this, into E, charge on electron. But we know I equals delta Q by delta T. But delta Q equals I delta T. For delta Q we can substitute NaLe. And for I, delta Q, I delta T equals NaLe. If you take delta T onto this side, NaL by delta T into E. L by delta T can be called as drift velocity because it is the average displacement by time taken. So drift velocity, from the definition of drift velocity, I equals NEA Vd, but I by A, if we take onto this side, Ne Vd, but I by A is J, the current density, Ne Vd. If we substitute for Vd, Ne into E tau by m into E, as we write it here, as Vd equals E tau by m into E. Therefore, J equals Ne square m by tau into E, or Ne square tau by m can be called as sigma E. It is again Ohm's law as we proved previously. Sigma equals Ne square tau by m is the expression for conductivity in terms of charge density, relaxation time, the tau, like that. But here, before concluding this session, we want to think of little bit about relaxation time. Relaxation time is the average time interval between two consecutive collisions of the free electrons inside the metal. Say, let us define it. Relaxation time is the average time interval between two consecutive collisions consecutive collisions of the free electrons in the metal. Say, if you want, I will just explain it a little bit. Say you have a free electron there. It moves like this and it collides with some ion there. It moves like this, it collides like this, it moves like this, and there's a collision, it goes like this. And there's another collision, it may come back like this. Say in first collision, it is for 1 second, for 0.1 second say. For second collision, 0.2 second. For third collision, 0.3 say, 0.1 second again. And fourth collision, 0.15 second like this. Say if you take the average of all these time intervals between two consecutive collisions, then we call that as relaxation time. So with these basic ideas and those derivations for J equals sigma E and sigma equals Ne square tau by m, we conclude this session. In the next session, we go for the temperature variation of resistance and all those things.